Hello everyone. When I was first asked by Torbjörn and Fedor to take part in the Working Group 1 meeting in Prague, I was a bit surprised. I'm not a taxonomist and not really a barcoding person, so I thought they made a mistake. Even more, I'm very happy that I could contribute to Working Group 1 and was asked to present you today the results of our gap analysis on monitoring relevant aquatic species in Europe. As you might imagine, such a gap analysis is a teamwork. Besides me, 40 other people from Working Group 1 contributed to it, many which will also present during this conference. The general idea of the gap analysis was to compile lists including all species relevant for aquatic monitoring in Europe, compare these lists against Barcodes reference libraries, and see for which species Barcodes are already present and where they are still missing. Two main directives regulate the monitoring of aquatic habitats in Europe. First, the Water Framework Directive concerning freshwater species, and second, the Marine Strategy Framework Directive concerning marine species. National contact points from 30 countries were contacted to obtain their monitoring lists. These were then filtered to include only species rank data. Taxonomic coordinators checked the lists for synonyms and spelling errors, and final checklists were generated for the comparison with the reference libraries. For freshwater, we obtained 29 national checklists. While most checklists included mainly species rank data, some, such as France or Spain, included mainly higher taxonomic ranks, such as family or genus-based data. For freshwater macroinvertebrates, we obtained 23 national checklists with species data, and overall 4,500 species were monitored. For vascular plants, approximately 700 species were included in our analysis, and for freshwater fish, approximately 600 species. For the marine monitoring, only very few national checklists were obtained. Hence, we used two alternative matrices. First, the ERMS, which is the European Register of Marine Species. It includes approximately 17,000 invertebrate species and 1,500 fish species. And second, the AMBI, which is a biotic index for marine habitats and includes approximately 3,000 European invertebrate species. For diatoms, we obtained approximately 3,700 species from national checklists. However, for several national checklists, it was not clear which habitat was referred to, not even if marine or freshwater. Hence, we also used the habitat which was most often referred to in national checklists, freshwater phytobenthos. It included approximately 3,000 species. In the next step, we compared the species lists against the Barcode reference libraries. We use the Barcode of Life data system BOLD as reference library for almost all species groups. For freshwater fish, we used additionally Mitofish and NCBI GenBank for 12S analysis. For diatoms, we used the Diet Barcode database. Coming now to the gap identification. What we see here are the results for the ERMS list. Each little square represents 50 species and each row 1,000 species. From the 17,000 species of the ERMS list, approximately 3,700, meaning 22%, have at least one barcode available. Comparing this to the other monitoring groups, we see that the diatoms have with 15% even a lower coverage. The AMBI with 48% and the freshwater macroinvertebrates with 65% have an intermediate coverage, while the marine fish and the freshwater vascular plants have with over 80% high coverages. For freshwater fish, CO1 has also a coverage above 80%, while 12S has only a coverage of 36%. I repeated the gap analysis recently to see if there were any major changes in the coverage for the different monitoring groups. For ERMS, AMBI, and freshwater macroinvertebrates, we see increases in the coverage of 4 to 7%, here highlighted in green. For the already well-covered marine fish and freshwater vascular plants, we see an increase of 1%. For diatoms, we see almost no increase at all. For freshwater fish, I think that the coverage of 12S might have strongly increased as it is now established as a meta-barcoding marker. However, obtaining the data is not that straightforward, and hence freshwater fish will not be covered much in this talk. Next, we analyzed how the coverage differs for the different taxonomic groups within one monitoring group, here the AMBI. What we see is that the coverage of most groups is between 40 and 60%, but that some groups have high coverages even above 80%, such as the Decapoda. Then we analyzed how the coverage changes if not only 1 but 5 barcodes are required for species to score it as barcoded. We did this as more barcodes will enable a more reliable species identification. We see a strong decrease in coverage to 20 to 30% for most groups. For freshwater macroinvertebrates, we see an even higher variation for the different taxonomic groups, ranging mainly between 50 and 90% coverage. Again, the increase from 1 to 5 barcodes decreases the coverage strongly, but it was still higher than 40% for the most taxonomic groups. We analyzed next how the coverage is in relation to the number of countries where a species is monitored. We see here the number of species monitored in the different categories of number of countries, and here how the coverage of the species is. If we look at the species monitored in 21 countries, we see that they have a coverage of 100% in the 2019 gap analysis, here in blue, and in the 2021 gap analysis, here in green. In general, we see that species monitored in many countries have a better coverage than species monitored only in a few countries. When we look at the freshwater insect species monitored in the different countries, we see that the Czech Republic has an exceptionally high number of species on its monitoring list. This also impacts on the coverage, as the coverage of the Czech Republic is much lower compared to the other European countries. As for the freshwater invertebrates, we also looked for the freshwater vascular plants, how the coverage is in relation to the number of countries where the species are monitored. And again, we see that the species monitored in several countries have a higher coverage compared to the species monitored only in a few countries. For diatoms, we see the same pattern, although here the coverage is in general much lower. Next, we separated the barcodes into 3 categories, depending on how easy the metadata can be accessed. First, we have bold public barcodes. For these barcodes, metadata are stored together with the barcodes and can be easily accessed. The metadata are, for example, the determiner of a specimen, its sampling location, or the sequencing institute. This can potentially enable to access the quality of the species identification associated with the barcode. Next, we have bold private barcodes. Here, the metadata are stored together with the barcodes, but currently not accessible. Normally, they will get available within a few years, when the barcode is getting public. But currently, we cannot judge about the barcode quality. Then, we have barcodes mined from GenBank. Here, the metadata might or might not be stored in GenBank or in an associated publication. While it might be easy for a single barcode to assess the metadata, if available, getting the metadata for thousands of barcodes might be very complicated. Looking at the ERMS data, we see that 42% of the species with barcodes have at least one barcode stored publicly in bold. Another 32% have at least one barcode stored privately in bold. The remaining 26% of the species with barcodes have only barcodes stored in GenBank. For the other taxonomic groups, we see similar patterns. However, the proportion of species having only barcodes mined from GenBank is lower. Looking into the different taxonomic groups within one monitoring group, here the freshwater macroinvertebrates, We see a strong variation in the coverage of three categories. For example, trichopterans and hemipterans have over 80% of species with at least one barcode stored publicly in bold. In contrast, annelids, arachnids, and mollusks have a high proportion of species with barcodes where not a single barcode has an easy access to metadata. Comparing the results of 2019 and 2021, we see a large increase of public barcodes, most likely because previously private barcodes are now publicly available. For freshwater vascular plants, two different barcodes are used, matk and rbcl. If the data are stored privately, we don't know which of these two markers was sequenced, while barcodes stored publicly or mined from GenBank have this marker information. In 2019, 63% of the species had both markers deposited, and additionally 14% had one of the two markers stored, mainly rbcl, while 5% of the plant species had private data only. In 2021, already 76% of the species have both markers deposited, mainly by an increase in matk sequences. Now, 6% have only a single marker present, and 2% of the analyzed plant species have only privately stored barcodes. For diatoms, we see that approximately 2/3 of the species with barcodes have both markers present. When we compare the number of countries where the diatoms are monitored to the coverage of the two markers, we see that diatoms monitored in several countries often have both markers present. When we analyzed the barcodes, we observed that several barcodes had reverse taxonomy as species identification method. So what does it mean? In general, we expect that a specimen is identified by a taxonomic expert, a barcode sequence is generated, and the species identification together with the barcode and the metadata are stored in bold. However, in reverse taxonomy, a barcode is generated for a specimen or a bulk of specimens. The barcode is compared against bold, and the specimen is identified. Then the barcode, together with the species identification and the metadata, are stored in bold. This might not be a problem for species which are well separated from other species in the same genus and if already several barcodes are present for the species. In other cases, however, it might impact the barcoding quality strongly. For example, if misidentified specimens cause misidentification of reverse taxonomy. So how can you see if the species identification of a specimen is based on reverse taxonomy? It's not that easy. If you look at the specimen page, you will not find the information directly. You have to look more closely into the metadata. There you will find the identification method and the term describing reverse taxonomy. However, there is not only a single term describing reverse taxonomy, but we found 76 terms in our analysis. Most often, bin taxonomy match is used, followed by bold ID engine and bold ID engine manual. There are also different writing styles of the same term, such as tree-based identification. This makes it even more complicated to identify reverse taxonomy, especially in the automation of an analysis. Next, we wanted to see how many of the barcodes are really identified with reverse taxonomy. We see that for worms, marine fish and AMBI, only a very small fraction of the public barcodes were identified by reverse taxonomy. For data stored privately or mined from GenBank, we don't know the identification method, so the real proportion might be higher. For Freshwater Macroinvertebrates, we see that 63% of all public barcodes and over 36% of all barcodes were identified by reverse taxonomy. For vascular plants, only 2 barcodes were identified by reverse taxonomy, so we didn't show the data here. When we look on the species having barcodes identified by reverse taxonomy, we see only a very low fraction for worms and AMBI. 10% of all species and 20% of all species with public barcodes have at least one barcode identified by reverse taxonomy in marine fish. For freshwater macroinvertebrates, 15% of all species and 31% of all species with public barcodes have at least one barcode identified by reverse taxonomy. We also characterized reverse taxonomy with potentially strong impact, as cases in which, for example, more than half of the public barcodes was identified by reverse taxonomy, or when a species had only 5 or fewer public barcodes and some of these were identified by reverse taxonomy. Looking more into details for freshwater macroinvertebrates, we see that a high proportion of reverse taxonomy barcodes originates from dipterans. But also annelids and coleopterans have a high proportion of barcodes identified by reverse taxonomy. Looking on the proportion of species impacted by reverse taxonomy, again a high proportion was found for dipterans and annelids. Here, the species were often even impacted by potentially strong reverse taxonomy. In contrast, for coleopterans, although many barcodes were identified by reverse taxonomy, only few species were impacted. Coming to the general conclusions. First, for the 31,000 analyzed species, 35% had at least one barcode present. The coverage depended largely on taxonomic group. There were still many species without barcodes for diatoms and for invertebrates, especially from the ERMS list. While freshwater marine fish and freshwater vascular plants had coverages of above 80% of the species. Generally, we saw that species monitored in several countries had a better coverage than those monitored in a few countries. Those monitored in several countries but still lacking barcodes are a good target for future barcoding initiatives and were partly already targeted in a Working Group 1 workshop. Concerning the availability of metadata, we saw that for 18% of the analyzed species, only private barcodes or barcodes mined from GenBank were available, so without easy access to metadata. This is approximately half of the species with barcodes. For vascular plants, a large proportion of the species had at least one barcode sequence for each of the 2 barcoding markers. But rbcl is still slightly better covered than matk. For diatoms, which have generally a low coverage, rbcl was also better covered than 18S. For reverse taxonomy, we saw that approximately 5% of all analyzed species and 17% of all analyzed barcodes are impacted by reverse taxonomy. However, the proportion might be even higher as we could only specify the identification method for public barcodes. The proportion of reverse taxonomy depended largely on the taxonomic group, with dipterans and annelids having very high proportion of barcodes being identified through reverse taxonomy and species impacted by reverse taxonomy. Overall, we identified 76 terms specifying a reverse taxonomy identification method. Here, a more uniform term could help to enable an automated detection of reverse taxonomy. With this, I want to thank Working Group 1 and all the contributors of this gap analysis for the very nice collaboration and you for your attention.